This diagram shows standard Ampere's law applied to a flat surface. When an analytical surface like S1 intersects a wire, the physical current I passing through it determines the resulting magnetic field. However, if we stretch that analytical surface into a bowl-shaped boundary, like S2 on the right, it spans the empty gap between the capacitor plates. No physical charge crosses this empty space. Under the original law, the enclosed current here is zero, meaning the magnetic field should also be zero, directly contradicting the results on our first surface. This mathematical contradiction proves Ampere's original law is incomplete when applied to open circuits. James Clerk Maxwell resolved this by identifying a growing electric field within the gap. He proposed that a changing electric flux over time creates a virtual current. This displacement current is the product of the permittivity of free space and the rate of change of the electric flux. During the charging phase, the physical conduction current in the wire equals this displacement current between the plates. Accounting for this virtual current bridges the physical gap, allowing Ampere's circuit law to function continuously across the entire system. Taking the time derivative of standard capacitor equations yields two practical formulas for displacement current, one based on the change in voltage and the other on the change in the electric field. In this problem, we are given a rate of change of voltage at 1 million volts per second and a total capacitance of 1 microfarad. Substituting these values into the voltage formula yields a displacement current of exactly 1 amp. Identifying known variables, voltage versus field, determines which formula from the toolkit is appropriate for the calculation. When given the electric field's rate of change and the plate's physical radius, capacitor geometry becomes essential. We must calculate the circular area before solving, substituting pi times 0.05 squared into the electric field formula. Spatial dimensions are a mandatory component when calculating displacement current through variation of the electric field. To calculate the inner magnetic field, we examine the region defined by this blue Amperian loop. These calculations depend on the enclosed current fraction, found by multiplying total current density J by the loop's area. Plugging this into Ampere's law yields the magnetic field. Magnetic fields within the gap are a function of localized current density, not the total current in the circuit. The final challenge is finding the displacement current enclosed within this outer annular ring. Because the electric field is uniform across the plates, current follows a constant density. Finding the current here means calculating the geometric area ratio between the ring and full plate. By subtracting the inner empty circle from the total area, we find that this specific region carries exactly 3/4 of the total current. The expanded Ampere-Maxwell law accounts for the sum of both conduction and displacement currents. Calculating that displacement current relies on 3 variations: the change in electric flux, the change in voltage, or the change in the electric field across a specific area. These 3 formulas provide the mathematical framework for how a changing electric field resolved a glaring contradiction in classical physics.